Okay, I think it's time to blast off. What do you think, guys? Yeah? Yeah. All right, to those of you at home, someone else has lost the phone, and to those of you here at Mind to Guide, would you please put your phones, your smart devices, into the app. You should see some text in front of you. This text, if your phone isn't working, smart device working. And if you look down to your feet, you see a home icon, and then you should see a little solar system. If you trigger, so that's push the right-hand button, and take yourself to our virtual solar system. Has everyone done that? Is everyone transported? You can tell because there's a giant ball of fire beside you. So myself and Katie are going to take you on a tour through this. This is interactive. If you've got a question, please put your hand up. We'll stop, we'll chat. And the same with you online as well. We're monitoring Facebook, Twitter, everything. Just using the hashtag cyber, ask us a question, and we'll be interrupted. So
we'll start our tour at the innermost planet, Mercury.
Let's do it.
So go down and look at the Mercury icon and click on that one. And there should be some text that shows up and a nice little image of Mercury.
In my universe, this is off to my right. You all look so cool right now, by the way, in your headsets. So there's Mercury on the screen if you haven't got it on your phone. This is a tiny world. This is a very barren, hot, and yet also freezing cold world because it's very close to the sun. Its daytime side gets very hot. Its nighttime side, because it doesn't have an atmosphere, gets very cold. It rapidly loses the heat. It's just like what happens when you don't have a cloudy night. In winter, it gets unbelievably cold here in Australia.
Yeah.
This place is minus 170. It's even colder than Canberra on a proper winter's night, right? It's pretty bad.
Because even though it's very close to the sun, there's nothing to bring the heat over to the far side. There's no atmosphere. It's just in the darkness of space. So on the far side, it's very cold. And it rotates really slowly. You'll notice in the app, it looks like it's sitting still. And that's because the rotation is really, really slow. It turns out that Mercury has this weird sort of tidal locking resonance thing where it gets 2 days for every 3 Mercury years. So 2 Mercury days for 3 Mercury years. That was right?
That or the other way around.
Or the other way around. One of those two.
Very long days.
Very long days. And so as it's going around the sun, it rotates very, very slowly. And so the day side and the night side don't switch very quickly. So one side gets extremely hot. It's staring at the sun for a very long time, and it only very, very slowly rotates around to get to the other side. So there's time for the rock to get extremely hot on one side and extremely cold on the other.
But even with all that heating that's coming from that daytime side, the overall world of Mercury is actually cooling down. Its core is shrinking as it cools, and it is actually getting smaller. It's lost about 10 kilometers in width over the last few billion years, give or take, which has actually caused these enormous cracks to form on the surface as it's shrunk. Now, I feel like we should continue our tour.
Yeah.
Yeah?
So,
everyone good? If you have questions, now's the time. Otherwise, it's like any sort of tour, like we're going to move on and then we don't get to go back on the tour and, you know. Okay. I will continue to enunciate even more loudly. All right. No, because you, are you not close enough? So the sun is actually showing a few graphical flourishes, shall we say, of real phenomena, including solar flares, coronal mass ejections, where millions of tons of hot atoms, that is a plasma or material, comes erupting from the surface. And if that slams into a world like our own with a magnetic field, that will cause a glow in the atmosphere, and that is the northern or the southern lights, the aurora borealis or the aurora australis.
And some of these coronal mass ejections are much larger than the Earth. It can be an extremely large sort of arc of material coming out, and if it's aimed right at us, then every once in a while it can cause really big problems for communication. So this has happened, I think, once in the last couple hundred years. There was a coronal mass ejection, enough hot plasma from the sun coming at us that it fried telegraph wires and shut down the telegraph system for a while. If it happened now, we would have bigger problems, but we're not entirely prepared for that, so hopefully it doesn't. It just, no, there's no, well, there's some,
you can see it coming.
You can, I mean, the material takes longer than the light, so you do see something coming, but the work that needs to be done to shield it is like hardening the electronics, which is not an overnight endeavor.
Think of nuclear war, EMP wipes out electronics.
Yeah.
That would happen globally. It would knock us back to the Stone Age, a big Carrington-style event.
Yeah, yeah.
So happy times. Shall we continue?
Yeah, this is why we're avoiding the sun. It's not a great place.
Yeah, that's right. We don't get too close. We'll fry electronics.
Yeah.
All right.
All right.
Let's go to that romantic world in the sky, Venus. There we go again. For me, it's just a little bit off to the right. You can actually see, if you look further right, all the other worlds do appear to be rotating, and rotating quite fast. Again, Venus doesn't seem to be moving. That's not a bug. It really is moving so much slower than the rest of the worlds in our solar system. In fact, it's actually spinning in the wrong direction, opposite direction, for reasons we're not completely clear on. We think it might be a planet did a flyby and maybe, you know, sort of didn't quite collide, but probably stole its orbital momentum around. No. But it's still a bit of a mystery.
So this image that you have in your app of Venus is an image of the surface of Venus. When we look at Venus in a telescope, we tend to see the cloud cover, and it's not a very interesting looking world, just the clouds, which is why we're not using that image here. But the clouds are just sort of a grayish, orangey sort of cloak around it. But the surface is a lot more interesting. But it's not a nice place to be. So we have sent probes to the surface of Venus. There have been a few landers that have landed on the surface of Venus. None of them lasted for more than about 2 hours. By comparison, we've had rovers running around on Mars for like a decade. So the problem with Venus is there are a couple of things. One, it's extremely toxic and has all these corrosive gases in the atmosphere, but the atmosphere is also extremely, extremely thick and very, very hot. So the pressure at the surface of Venus is something like 90 times the air pressure on Earth, on the surface of the Earth, and the temperature on the surface of Venus is hot enough to melt lead. So it's really a very unpleasant place. It also has clouds made of sulfuric acid that rain sulfuric acid, but it's so hot on the surface that the sulfuric acid will evaporate before it hits the ground. So at least you don't have to worry about the sulfuric acid actually hitting you. It's just sort of in the air as a vapor.
It's burning your nose, eyes. Yeah.
So it's a very interesting world. It's sort of a sister world to the Earth in the sense that it has the same kind of, you know, topography. Like there's like rocks and mountains and things like that, clouds, all of that, the weather. But it's not a nice place to be. Yep. It's had this runaway greenhouse effect. Something made the planet get this extremely thick atmosphere, extremely hot surface, very, very high pressures. It's I don't remember the percentage, but it's mostly CO2 is the atmosphere. Yeah.
So, oh, by the way, I should point out, we do have a couple of books to give out as prizes for. You take your headsets away, by the way. This is already one prize up. So well done. All right. So Carl Rombos, thank you for the designs. Adam Spencer gave us a few books of his as a little prize for the best questions. So keep that in mind. If you're not already incentivized enough, you get a free book as well as a free headset. So, you know, how good is that? No, that didn't come up. As of now, it was a good question, but only now they were. Now, Venus, one reason that Venus glows and looks so beautiful, so bright in the night sky is because those clouds of sulfuric acid reflect light really well. So next time you remember back to Venus, the goddess of love, the Greeks, turns out they weren't quite capturing the true nature of this hellish world that would melt you from the outside and, you know, make your life a living hell.
Crush you.
Or did it? I don't know, Sarah. Anyway. She didn't hear that, that's fine. All right, so anyway, so we'll escape Venus. Even lighter. Oh, wow. Okay. This is going to be, my throat is going to be ruined. All right. Is it time to leave Venus? Yes? Our tour continues. All right, let's go to Earth. We all know it. We all love it. Oh, I've just seen it go from a new moon, and it's beginning to, oh, let's see where we go. So you'll see the moon's going around the Earth. Everything is in the right time in terms of the rotation of the days, in terms of the rotation of the moon. Basically, it's a few seconds per full day rotation, and everything else is scaled to that. So it looks a bit manic, but yeah, just like this talk, it's going very quickly. Oh, and that was a massive coronal ejection. Just came left to center and struck the Earth. Okay, so what we've just seen actually happen is the moon is passing just there between the sun and the Earth. If the alignment is exact, we can actually get the moon blocking the sun, causing what? Yes, a solar eclipse. And for those lucky few, which is, I think, maybe like 20 million people or something in America, who lie across that totality line, they will see that beautiful alignment.
And for a few lucky ones of us who are flying to America on Saturday in order to be there in time for the eclipse.
I'm so jealous of that. Okay.
So it might be cloudy. Who knows? We'll see.
I'm hoping so. I'm hoping so. So what makes Earth so unique amongst all of the worlds of our solar system, and indeed all of the planets, exoplanets, the worlds around other stars, so far as we're aware, is that it has, of course, life, but it also has some other interesting features that may or may not be a coincidence with us having life here on Earth. And that includes an ocean, that includes tectonic activities, so the movement of the plates, includes a protective magnetic field that shelters our atmosphere from the outbursts, those coronal mass ejections from the sun. And it has a moon. I don't think that's probably that important.
I mean, yeah, it's hard to say. There have been theories that the moon is necessary for life because it creates these tide pools that wouldn't happen otherwise. And who knows? It's unclear. But there are some theories that life didn't start in little pools on the surface, but rather at hydrothermal vents deep underneath the ocean, which has nothing to do with the moon. So. Yep. We don't know, but there is some really cool stuff about our moon. You will notice if you look at it in the night sky, it always shows the same face to the Earth. That's because it's tidally locked, so it rotates one full rotation every time it goes around the Earth. So it's always showing the same face to the Earth. And this is something that happens when you have a smaller body orbiting a larger body, close enough for long enough. It gets this tidal locking, so that it always faces the same face toward the Earth. In a very, very long time, the Earth will become tidally locked to the moon as well, and the Earth will always show the same face to the moon. That will take a really long time to happen, maybe longer than the life of the Earth itself, but we'll see. Oh, questions?
Yep. Oh. Sorry, what was that?
Why is it spinning so much faster?
Why is the Earth spinning so much faster?
Yeah.
So go on, man. You get a book. You get a book. Round of applause. Okay, you get a book and several claps, but not many claps. So the Earth appears to be rotating so much faster than the moon?
Yeah, so
No, just in general. Oh, so far. Yeah. Mercury, we have this idea of tidal locking. It's not quite there, but it's definitely getting slowed by the sun's influence. Venus, who knows, probably a near-miss collision, robbed it of its spin. The Earth has its spin. It's the first normal world because we're about to see some of the others rotate even faster, especially Jupiter, as we'll get to that. Any more questions on Earth? Yep.
Does it mean then that if it's a full moon, the moon rising corresponds to the sunset?
Yes.
Just repeat the question.
The question was, if it's a full moon, does the moon rising correspond with the sun setting? And yes, that is true. So in a full moon, the moon is on the opposite side of the Earth as the sun.
Oh, wait, let's do it. This is the sun.
Okay.
You're the Earth.
All right, I'm the Earth.
And I'm the moon.
Okay.
Resplendent, radiant.
Okay,
And we're
so that's-
exactly in line.
So that's a full moon, and then if you come over here. All right, so now,
Nice, an eclipse.
well, okay. But it's a new moon if you're not exactly aligned.
Because I'm in shadow.
Yeah, so
My
when
face
the
is-
moon is a very thin crescent in the sky, it's closer to where the sun is in the sky. When it's a full moon, it's opposite.
Yep.
And when it's a larger moon, it's, more in, the middle of the night, kind of. Yeah. Sorry? The red moon. Ah, that's a lunar eclipse.
Oh,
Yeah, so let's see, how do we get it? Okay, so lunar eclipse. So this is a
I am being shadowed.
So this is a lunar eclipse. This is where the moon is in the shadow of the Earth. And the reason it looks red is because the light from the sun is sort of filtered through the air of the atmosphere of the Earth, and it sort of filters through and shines on the moon.
and we all know that what color is the sunlight as it goes through all the atmosphere is red. That's a sunset.
Yeah. So
a
from the
sunrise.
moon, so the moon is then seeing all the sunsets and all the sunrises on the Earth at the same time.
Very romantic.
Yeah.
Yes. Oh, does the moon have magnetic field?
Okay, so the moon does not have a global magnetic field. It has little pockets of magnetic field, and it's really interesting. There's really interesting history around that. There are some little pockets of magnetic field that are exactly opposite of big craters on the other side. So there could be some kind of mechanism that's pushing out little bubbles of magnetism across the moon through the middle. There may have been a magnetic field in the past in the moon, so there's some sign that there may have been some global magnetic field in the moon's past. But at the moment, there are just these weird little pockets. And you can actually see in certain images of the moon, you can see little lighter wispy regions that are places that are shielded by local little bubbles of magnetic field. And so the other parts get darker because they get hit by more particles, and then those parts under the bubble stay a little whiter. It's really cool stuff. Yeah.
I did not know that. Awesome. Who's asked that question? Yes. Okay, I think you get that because I learned something just now. So thank you very much for the question. All right, let's continue our journey to the world which will one day surely attack us. That is, of course, Mars, featured in many of your favorite sci-fi films. For example, The Martian,
Yeah.
famously.
That's a good one.
It is, of course, the only world entirely inhabited by robots, which I think is one of the coolest things I know in science. Mars is much smaller than the Earth. Its gravity is about 40% of ours, and that means that if you were to live on Mars, you would grow potentially much taller, but certainly your body would be much weaker. You wouldn't have as much muscle density, your bones might be more fragile. We know all this happens under weaker gravity because our astronauts, when they've gone into microgravity in orbit, waste away. And by the end of a year in orbit, even though they're pumping iron all the time up there to try to keep themselves strong, they can barely walk when they land. So if you go to Mars after 9 months of travel, chances are that, small step for man, giant leap for mankind. Small step you could probably manage, giant leap, very unlikely, you'd probably break your hip. So it's a very different type of experience to get to Mars than it is, say, the moon. Not that I don't think we'll do it, but I suspect it's a little harder.
There are some challenges, and one of the challenges about going to Mars involves magnetic fields again. So Mars does not have a global magnetic field either. Mars probably had a global magnetic field in the past, and having a magnetic field is a really useful thing for a couple of reasons. One is that it shields you from harmful radiation from the sun and from cosmic rays. The other one is that it holds on to your atmosphere a little better. So if you lose your magnetic field, you can also lose your atmosphere, and that appears to be what happened to Mars. It used to have an atmosphere. It used to have liquid water flowing on the surface, as far as we know. But something happened, and unlike Venus, which got more thicker atmosphere, Mars lost its magnetic field, lost its atmosphere, and now has a very, very thin atmosphere, something like 1/100th the thickness of the Earth's atmosphere. It's very, very cold most of the time on the surface, although it does have seasons, and it can get to a little bit above freezing at certain
It
times
can
of year.
get to 25.
Yeah.
That's pretty.
Yeah.
That's all right.
Yeah.
I'm from Ireland. That's a real good summer's day.
But you still, but you still die because there's not enough air to breathe. It's mostly carbon dioxide. And the fact of not having a magnetic field is one of the big challenges if we ever want to go to Mars, because we will not have that shielding that we need. And we don't have currently good technologies for artificial or, synthetic things to do the shielding.
That's right. So as well as your muscles wasting away and breaking your hip when you land, you've probably also been riddled by cancer. So win. Yep. Okay, great question. Why are there sandstorms if the atmosphere is so thin?
That could get a book.
Yeah, go and get a book. Everyone gets a book. It's like Oprah. Thanks, Adam Spencer. So because the atmosphere is so thin, you can actually, anything, I guess you throw up, maybe change the phrasing of that. The material that you throw into the air can sort of hang around, persist. The wind speeds can get very large, so they can carry material high and for a long time.
But also the sand can be part of the sand. Some of the sand is very, very fine. So that's actually another problem with going to Mars, is that there's this extremely fine sand that would just get everywhere and could actually be quite toxic to breathe in. So if you walk around outside and come in to your little habitat and you track some dirt in, that could really harm you. So you have this extremely lightweight, thin sand that gets whipped around in these fast winds. There's also lightning. There's dust devils on Mars. All sorts of cool stuff.
I do want to say though, The Martian, wonderful film that it is. One of the things that it does wrong is that the global sandstorm, which can happen, you can have an entire world-sized sandstorm. The entire world goes essentially invisible to us as the sand picks up. The wind might be at speeds of hurricane speeds, but it doesn't have hurricane force. Yeah. Essentially because it's moving very fast, but there's not much of it that's moving very fast, so you sort of feel it like a little breeze as opposed to like, oh God, everyone's left me behind, and I'm Matt Damon. And that's the kind of... Imagine if he was following this. How weird would that be? All right, anyways. Yes, right at the back. Yep.
Or would the money be better spent on, say, like a moon outpost?
Oh, okay. I love this question. The question was, should we be putting in a lot of the resources to get to Mars? Very expensive. Or should we be trying to instead build a moon base or get to the moon at least instead?
Oh.
I don't think they're mutually exclusive.
Yeah.
Or at least I think getting to Mars, you have to, as a first step, get to the moon again, practice your technologies at least.
It can help. There are different opinions about whether going to the moon first helps in getting to Mars, because they're kind of different procedures. But I mean, the moon is just much less interesting. I mean, Mars is really cool. Mars might have had life in the past. It had flowing liquid water on the surface in the distant past. There could have been life. The conditions on the surface are a lot closer to what Earth has. The gravity is a lot closer to what Earth has. It's only 1/6 on the moon.
It's also got almost exactly the same length day, weirdly.
Only 40 minutes or so longer.
Yep. Oh, those are good. Look, I personally, and I'm really excited by this, the European Space Agency's concept of the Moon Village. They are basically building the infrastructure on the moon whereby other countries can land a habitat and connect up power and, I don't know, whatever else, internet, Netflix, probably whatever is necessary for life. And as a result, hopefully spur that sort of development, and certainly with private companies. Mars, just imagine if we did see someone walk on Mars. Katie, I don't know.
Yeah, I'll go.
No, I mean like you. Yeah, that's right. Yeah.
No, I'll go. Yeah, send me now.
Right at the back. Oh God, is it true? Oh, I love it. Katie, I'll ask you this. Yeah. Is it true that the Curiosity rover sings itself happy birthday to itself?
So I don't think so.
Oh, come on.
It doesn't have a microphone, for one thing.
It uses like its equipment
to buzz. A little piezoelectric.
I don't know. I don't know. I don't know for sure. I think it's probably a myth, but I don't know.
Why don't you go and find out?
Yeah, well,
That would be worth the journey, right?
I'll
Yeah.
check on it. I'll get back to you.
Okay, I have heard that,
I've heard
and
it.
I know you have too,
Yeah.
but I think it's a good story. Even if it's not true,
Yeah, yeah, I don't know.
NASA, you've got to upload it, the software if it's not, that it hums to itself happy birthday alone on an alien world. And Sarcastic Rover, I'm pretty sure, yeah.
Yeah.
Follow the Twitter handle Sarcastic Rover because he is that person, whoever that person is, tweeting as the rover, has certainly done that, and it's one of the most tragic things I've ever seen. Yeah.
How come all the planets' orbits are on a relatively flat plane?
How come all of the planets' orbits on a relatively flat plane? Can you? I would totally give you a book for that. That is a wonderful question.
Can you pass this?
Round of applause. Well done.
Thank you.
Do you want to take it? Cosmic
Yeah,
pancake.
sure. Yeah. So the reason for that is that the material that made up the whole solar system was in a disk in the beginning. So the way that stars form is that you have a sort of cloud of gas comes together, and there's sort of random motions in this cloud of gas. But then as
I'm trying to help.
okay,
you.
yeah. Okay, so there's random motions, but there's some sort of bulk rotation. There's some sort of average rotation in some direction and on some plane. And so as the cloud of gas is moving around and everything's moving around, the rotation in other directions gets knocked out. So like there's, two particles going this way, they hit each other, they sort of collapse into the final rotation. So over time, gravity and spinning creates disks. And this happens for all sorts of collections of gas and dust and stuff in the universe. If you have a lot of spinning, you get this with galaxies. Galaxies create disks, and you get this on the scale of stars as well. So you form a disk first, and then the stuff at the center is the most dense. That forms the star, and then there are little sort of eddies in that disk, and things collect together and form planets. And so the planets form out of that disk, which is why most of them are going, in the same direction around the star,
Yep.
and why they have some spinning of their own. So that all comes from forming in a disk. There are things that can knock things out of that plane. So there are some bodies in the solar system that are orbiting in slightly different planes, like some dwarf planets are not exactly in the plane, but the planets themselves are mostly in that plane.
Ah.
The big stuff stays in the plane mostly.
We may have to continue our tour because we actually have a whole universe to show you as well as just the solar system, and I haven't been keeping track of time again. Can I get a time check, someone? 7:20. It's 7:20? Oh, wow. All right. At light speed then. We're going to go to Jupiter, king of the planets. It is absolutely whizzing around. This orbit takes about 10 hours, that is Earth hours, for 1 day. This is why it's moving so fast. Jupiter is just absolutely awesome. It's just a giant ball of gas. Composition similar to the sun. It has storms that are larger than the entire Earth. This is the Great Red Spot. These bands of color you see are different types of chemicals. Some of the colors from chemicals we don't know. We can't recreate those conditions in the lab to make those chemicals, to check what color is actually, what chemical is actually creating that color. It's just a really awesome planet, and we're getting super close-up views of it thanks to Juno. So go to Juno Cam, and anyone at home watching this, Juno Cam, check out the latest images from NASA. You can choose where the Juno will point its camera to look, what features to probe, as well as just generally being an awesome satellite discovering new things about Jupiter, like the fact it doesn't appear to have a core, has some weird thing, we're not sure what, but you fall through gas, and as you get deeper and deeper into the gas, it's getting denser and hotter, but it's never quite becoming a solid body like a rocky surface. So you would just keep falling through something, and it's a something because we actually don't know still at this stage. Juno's not had the decisive word yet on what's actually going on deep beneath the clouds.
But it has found some really weird things like layering in the clouds that was not expected. Different. They're checking out the magnetic field, and the magnetic field has these weird properties as well. So
it's super
so
weird.
read up on Juno, the spacecraft. It's doing really amazing things. What it's doing is it's orbiting. It dives in really close, and then it goes really far away. And the reason it's doing that is because the magnetic field on Jupiter is really strong. And so there's this high energy magnetic field and these particles, and it's a very dangerous place to be, lots and lots of radiation. So the spacecraft goes in really close, takes pictures, and zooms out again and comes out, and then it zooms in really close and zooms out again. And it's just doing that kind of orbit over and over again and taking pictures and getting data, and it's a fabulous project.
To put it in perspective, if Jupiter was the size of, say, a basketball, then the Juno spacecraft is skimming just millimeters off the surface at incredible speeds, some of the fastest speeds we've ever attained as a spacefaring species. Everything about this mission I love. I think you love too.
Yeah,
so do check out Juno. We're going to have to continue because, go on then, one question. Yep. Why doesn't the red spot move?
Well, it rotates with the rest of the planet. So if you look in you can kind of see it zooming by.
It's so quick. Look how quick that's going.
But why doesn't it move across the surface? Yeah, we don't know.
It's stuck between bands.
Yeah, but it's been there for like a few hundred years at least. It's getting a little smaller, but we don't know why it persists. We don't know how it got there. There are other little storms on Jupiter that are also persistent, and we don't know why those happen. There's a lot to learn about Jupiter still.
But you could imagine the Great Red Spot being like a ball bearing between two tracks, like sort of, I don't know, running track things, kind of thing. Well, that's called.
But yeah, so the bands kind of move across.
That was great.
The bands kind of move across in sort of different ways, and it moves. It does move. I mean, it's hard to define a reference frame because some of the bands move at different speeds too.
Oh, some of them go the other way, right?
Yeah.
It's a total mess.
So the surface, I mean, there's no surface, so it's not like there's no like solid body rotation in Jupiter. It does spin on average, but then parts of it move relative to each other. So it's just a really weird world.
Yeah.
Yeah.
I think we're getting that. The sense of confusion about it, certainly for me, is real. Right.
So we go to Saturn.
We're going to have to skip that question because we've got to go to the poster child of the solar system. That show-off planet, Saturn. If you go to there and you look up, Mark did a very nice job, I think, of the angle of this where we get to see Saturn and, of course, its rings, which is a collection of rock, ice, dust. It's glittering in the sunlight. That's what we're seeing, reflected sunlight from countless chunks of rock and ice in particular. The entire system of these rings is bizarrely delicate. The diameter from one edge to the other is about 120,000 kilometers, an impossible scale, much, much larger than our Earth. But its thickness is no higher, it's no thicker than this building. If you imagine something this high just extending for 120,000 kilometers, you can't, because that's insane. But what you can do is make a sort of an analogy, which I think is going to go better than I when I used it with that group of school kids, which is a vinyl record. Does everyone know what a vinyl LP, right? If you were to scale those rings down to the thickness of your vinyl record, then that vinyl record, to stay in proportion, would have to stretch out to about 40 kilometers or so. The entire thing, just this wafer-thin structure, incredibly delicate, kept clean by moons that are swirling around through their gravity. It's actually hoovering up the material. If we go back, you can see there are bands, there are structure gaps in the rings. And when we take a close-up look, in particular with the Cassini spacecraft, we see there are those little shepherd moons that are cleaning up.
And some of those moons get close enough to parts of the rings that they can create waves in the rings, both waves sort of in and out and up and down. And so you can sometimes see these sort of long shadows of material that's been pushed up and down from that plane by the motion of some of these moons. So you can get little ripples, you can get sort of weird sort of lines from orbital resonances. It's very, very cool stuff. I mean, what you should do is you should go to the Cassini spacecraft webpage and look at the images and just flip through some of those pictures of the rings and the Saturn system. It's unbelievably beautiful, and Cassini is doing incredible stuff. It's actually orbiting between the rings and the planet at the moment and getting pictures inside that gap between the rings and the planet. And in just a few weeks, yeah, about
15th September.
About a month, on the 15th of September, it will get even closer to the surface of Saturn, well, the atmosphere, I guess, of Saturn, and go into a depth plunge and burn up in the atmosphere of Saturn and take data as long as it can as it's burning up in that atmosphere. So
very sad.
we only have a little while longer with Cassini. Check out its data. Look, follow it on Twitter and Instagram and everything. Really amazing pictures.
Stunning. All right, we've got some questions. Yes, sir.
So I'm jumping ahead of planet, but why does Saturn and Uranus, why do the rings go around?
We'll totally have to, we'll get to
we'll
Uranus
talk about
in
that.
a second, yeah. Yep.
Oh, that's a great question.
Could you repeat it?
Yeah, the question was, if something like a comet were to go in and ruin the rings, what would happen?
They'd repair over
Yeah,
time.
so over time, so the rings are held together by the gravity of Saturn and the sort of the way the gravity changes over time. So if you have material orbiting in that close to the planet, then it gets sort of smushed out into these rings. You get a disk in the same way you get a disk with a lot of other things, and it's pulled by
That early forming solar system.
yeah, and so it's pulled flat by these tidal forces, which are sort of differences in gravity between different parts of the ring system. So if you did destroy some part of it and disturb it, it would reform over time. Also, if you tried to put a large moon closer than the rings, it would smear out and create more rings. So that's sort of a property of the gravity of the system.
All right, we have
I think
loads of
that was a
questions
good
in very little
question.
time.
I'm-
Yeah, no, totally. That was a good question. I totally forgot we had books. Sorry, Dan. Yes.
When you say the moon
There you go.
cleans the moon, how does that predict?
Okay, so these shepherd moons clean the rings, the binaries, by their gravity. Their gravity actually pulls material in. So the material is raining down on the moons. And there's actually a beautiful close-up view of Pan, I believe, which essentially has, because all of the material is coming in on this like knife edge, the rings are so thin that it all just keeps landing on the same on the equator, essentially. So you've just got this mountain range built up on Pan going right around the equator, where it's just hoovering up material constantly from that same direction, from these rings. And it gives it looks like ravioli. It is so sad. It's majestic ravioli, space ravioli.
So I want to do just one shout out, because there is at least one moon that is creating rings from the moon itself. So Enceladus
Oh, of course, yeah.
Enceladus is one of the moons of Saturn. It's one of the larger ones. It has plumes of liquid water, sort of icy water coming out of the poles. There's cracks in the surface. It has an undersurface ocean of liquid water under the ice, and there are little cracks, and there's this sort of liquid, or vapor or ice, sort of flowing out the poles, and that stuff, as it comes out, creates another ring, sort of very wispy, very faint ring going around the planet from the stuff coming out of the moon. So it kind of goes in both ways.
And it's worth pointing out, there are more oceans underneath the ice of moons in our solar system than there are oceans on planets. Because
Yeah.
we're the only one with an ocean under an atmosphere, and there are 2 moons that we know of, and we suspect there's probably a bit more actually.
There's several.
Yeah. Around Saturn and Jupiter. So twice more places for life to exist than there are on planets in our solar system alone.
And the amount of water is also, there's much more water in, like, total amount of water in these undersurface oceans on these little tiny moons than there is water on the surface of the Earth.
Yeah. Okay, last question on Saturn, and we'll have to.
Two of the rings you're showing us, is at an angle to the plane of the planets. Is that just so you can show us, or
No, it is actually at an angle.
so why
Yeah.
is it at an angle?
Why is it at an angle? So the rotation axis of the planets, they're not all perfectly aligned with the up in that disk. Ours is tilted, and so is Saturn. So at different times of year, we see when we look at Saturn from the Earth, we see the rings at different tilts because of the way that the planet is moving around on it with its axis tilted. So it's actually kind of cool. Right now, it's tilted almost like the maximum. So if you look at an image of Saturn in a telescope right now, you see the rings, much more sort of flayed out, not side on, but like other.
Almost face at maximal extent.
Yeah, maximal extent. Yeah.
Alrighty, we're going to see. So Saturn, we've just heard, has seasons just like the Earth. We're going to go to somewhere that doesn't, or at least doesn't change, and that is Uranus. So if we jump to Uranus, for me that's behind, so that's going to be. There it is. Everyone seen it? This is not a mistake. Mark keeps his job for another day. And that is because Uranus really is on its tilted, it's on its side. The orbit is spinning, the rings are orientated completely on their side relative to the rest of the solar system. The North Pole points directly at the sun. It's always summer in the north. The South Pole is always pointing away. It's always winter.
Night.
Nighttime.
Yeah.
Yeah. Oh, yeah, sorry, no season. Whatever. Nighttime. It's really cold. Like, oh my God. In terms of like the idea of winter and sun, it's very much minus a lot.
Yeah.
It's not a great, that was technical, I know, but it's really cold. For me, it's the rings, though.
The rings are
We only relatively recently uncovered the rings as well. I mean, like in the last few decades.
Jupiter has very faint rings
Very
as well.
faint, yeah.
We have a question in the back. Why don't more planets have rings? So it's easier for a larger planet to have rings because it's easier to sort of tidally disrupt stuff. But
if you collide things together,
Yeah.
they're going to form more dust, more ring material.
yeah, and if you have like it would be hard for one of these big planets to have a moon orbiting close without it getting stretched into a ring. So I think that one of Mars's moons might be destined to become a ring in the future. It is being pulled apart by the tidal forces, the gravity difference from one end of it to the other. So that'll become a little faint temporary ring. The bigger planets, it's just easier to make them on the bigger planets.
Yep. It's not to say that you can't have structures we usually associate with planets around smaller objects. For example, we have asteroids that have their own moons that go around them. What we see happening in the solar system happens on a number of ever smaller scales too.
Yeah.
It's just that very occasionally astronomers get particularly worked up about it and decide to earn the hatred of school children everywhere by calling some things planets and
Look,
some things
it
not.
was a reasonable choice.
Hey, I'm not defending it, man.
Right.
Let's not bring it up.
We have one more question before
We'll
we
lose the
go.
audience.
One more. Okay. Yes.
Yep.
Does space junk have the potential to form rings around?
Great question. Does space junk have the potential to form rings one day? Essentially, it kind of is a ring already.
Well, there's like several
There's a
rings
lot
in
of
different
rings.
planes, sort of. I mean, well, but it's not.
Eventually,
It's not on the same plane. Like you have to have a lot of material to make a ring that's noticeable. But it's just a haze, and it's really problematic.
yeah. So the space junk is going, in all directions, all orbits. It really is a sheet. But there's definitely some orbits are more popular because, say, they go over America and give telecommunications to America, and when that debris that forms from those satellites, defunct satellites, stays in those kind of orbits. So there are definitely preferential places that there's more junk than not.
Yeah.
And yeah, with enough of it, you could form a ring, for sure. I mean, it would look awesome, right? I mean, it'd be terrible for space travel, but look amazing. So, silver lining and all that. But
Should we move?
yeah, because we have one more planet in our solar system, and I mean that very Very carefully, I've chosen those words. This is Neptune. It was predicted by mathematics. So we had the idea that Uranus's orbit was a little weird, something you could explain the slight changes in its orbit as if there was another more distant large planet pulling on it in its orbit, and essentially this prediction was made. Telescopes returned a couple hundred years ago. Neptune was discovered. This is a very super weird world because it actually has the fastest winds in our solar system. And it's actually, the winds go faster than the speed of sound on Earth. So your actual plane that you would fly in, 747, you name it, it couldn't actually make any progress in Neptune. As it tried to fly through those winds, it would be pushed back. This is a very strange world. We don't know what's powering winds that can be that fast.
It also has some persistent storms. There's a blue spot on Neptune that's been around for a long time, and so it also has the capacity to form these superstorms. But I guess it doesn't have as many sort of colors and chemicals.
Yes,
we haven't studied it. We haven't studied it as closely as the other Jupiter or Saturn. So there's still a lot we need to learn about Neptune.
Okay, this will be one question, then we're going to have to leave the solar system. Yep.
Neptune is.
Neptune has, you say, it has a strange magnetic field and it forms arcs? Arms? Oh, I didn't know that.
I don't know a lot about the magnetic field on Neptune. Sorry.
It would be a difficult one to probe. It's quite hard to measure magnetic fields that far as well. So, yeah, I'll have to look that one up. I'll take out the notice. All right, very last question at the very back then, and then. Yep. Oh, yes. So, yeah. Okay,
That's a good question.
so the tectonic activity that rejuvenates the surface of the Earth because essentially older crust gets, pulled down, or new crust pours over the top of it in lava. Does that happen on other worlds? No.
No, none of the other planets have active plate tectonics. Some of the little icy moons have surfaces that resurface through some kind of shifting and melting and cracking and stuff, but none of the planets have any plate tectonics that we know about. Mars used to have active volcanoes. It doesn't anymore. Some of the moons have active volcanoes. Io has very active volcanoes. Sorry? We don't know enough about exoplanets to know if they have that. We're still just at the point of, occasionally we can study the chemical composition of the atmosphere of an exoplanet, but that's about as detailed as we can get.
All right. So everyone, I want you to just look to your left and gaze back at our solar system. This alignment, were it to happen, would spell the end of our civilization. I'm just kidding. One, it wouldn't matter. Two, it doesn't really happen. But anyways, now we're going to go and transition to a view of the night sky. So if you go to home, so click on the house, and then we're going to go to the all sky viewer. Yeah, trippy, huh? All right, I want you to ignore that, and instead we're going to reference ourselves to cosmologists like myself and Katie. This is what the universe does and should look like. Instead, we're going to go to visible. So I want you to just go to your feet. To me, it's about 4 o'clock on the dial, and trigger off visible. And there you'll see our Milky Way, which is a beautiful image. It's a plain of gas and stars. The dark regions are clouds of gas and material that block the light from some of the hundreds of billions of stars that exist in our Milky Way, our sun, of course, being just one of those. The entire structure is this pancake that Katie mentioned happens around stars as they form their planets from it. So too the galaxies, and of course so too the rings of Saturn. So we see the same physics on a range of scales, and that's because gravity is scale-free. But anyways, I don't know why I started going on that tangent. Ignore that statement. Anyways,
if you look toward the center of the Milky Way, which is kind of over here, if you look toward the sort of bigger bulge part, that part is hiding the central region of the Milky Way. So we are sort of out on the edge of the Milky Way. The disk is
It's an
over here.
unfashionable arm.
Yes, of the western spiral arm of the
yeah.
galaxy. So in the central bulge of the Milky Way, there are lots of stars, lots of gas, lots of dust, and a supermassive black hole. So right in the center of our Milky Way, we have a black hole that's 4 million times as massive as our sun. We call it Sagittarius A star because we're very creative that way. It's not dangerous. It's not going to suck in the whole galaxy, but we do get to see stars orbiting around it, whipping past it as the extreme gravity of this black hole pulls onto it. And there was even a report recently that we were able to see effects of relativity as the stars were going past and the orbits were being affected by weird effects of the extremely strong gravity of that black hole.
And if you want to hear more about that, tune in to OzGrav on our Twitter feed and Facebook page, where we actually have people who know lots of stuff about this, studying that kind of thing. I hope, Matthew, that's okay. That was a good plug. Good enough plug?
Has the experiment have been installed?
No, that's the dark matter
Dark
one.
matter.
We'll not talk about that. Because we can't see it. Dark matter is invisible, so it made for not riveting content for a VR display. Now, just before we switch wavelengths of light, I want you to look to your bottomy right, and there are two faint smudges of light, so collections of stars, clouds of light or stars. These are some of the nearest galaxies to our Milky Way, the large and the small Magellanic clouds, as they're known, in Europe in particular, but these clouds are actually entire galaxies, smaller than our own Milky Way. In fact, they're going around our Milky Way and are in the process of being destroyed by our Milky Way because galaxies grow larger by cannibalism. They feed off other galaxies, and eventually, over many millions of years, billions of years, the stars and the gas of those satellites will be added to our own stockpile, and the Milky Way will be a little bit more smug, basically, and show no other signs.
And we are very fortunate here in the southern hemisphere that we can see these Magellanic clouds. If you're in a very dark night, you can see these two little sort of fuzzy dots, fuzzy smudges in the sky of these two little galaxies, and we can see the center of the Milky Way. In the north, you can't see any of that. So we do get a different galaxy that we can see in the northern hemisphere, but we can't see these.
Okay, I want you now to you don't have just to press the trigger. You don't have to look at anything, just press the trigger, and you should change the color of light. We basically have 2 minutes and I do the rest of the universe, so it's going to get very quick. There's lots of information in this app. There's many things we're not even going to show you. Mark has cried to create, and Carl has magnificently recreated black holes, for example. You're never going to see that in this tour, but you get to take this all home with you to explore at your leisure. This is a different frequency of light. This is in H1, we're seeing the H1 4-pi survey. So now we're seeing what were those dark clouds of gas that were black, that blocked the visible light. With a radio telescope, they glow brightly, and the stars are actually essentially invisible. So we're seeing the gas now of the Milky Way disk. This is, for example, what the Parkes radio telescope, the famous dish, sees. And you can see to the bottom right, the large and small Magellanic clouds are visible. That means they have gas. The Milky Way hasn't been able to steal it all yet, but it's trying. And there are actually streams of material pouring from those systems, and indeed other smaller satellites. Naomi McClure-Griffith has created a beautiful survey, for example, over east, looking at this. Now, click the trigger. This is infrared light. This is glowing gas and dust, essentially the heat. Now the gas is being warmed by the stars. Again, you can't make out the stars themselves as easily. And then I want you to click once more, and this is just a beautiful image. This is from one of the latest telescopes in Australia. It's built in Western Australia. It's the Mercury Wide Field Array, very long wavelength of light, radio waves, hundreds of megahertz for those who care. This survey is essentially a prototype for the square kilometre array, or at least part of that. What we're seeing here are exploding stars. Those points are exploding stars. Supernovae remnants, shock waves of material blasting into interstellar space. And in fact, Oh, there it is, beautiful. If you look up above the plane, see that thing, that massive thing? What is that thing? Anyone want to take a guess? Who said that? What? Black hole. Yes, this is a black hole. Well done. Except, of course, it's the jets from the black hole, which is what, of course, you meant there, yeah? Yeah? Excellent work. This is a material that's swirling around the black hole. Centaurus A is being blasted outwards along the poles, firing many, many light years, thousands, millions, whatever, huge amounts of distance into space that you can see. I want you to see. Did you want to add something?
I just wanted to say, so this is the sort of thing that can happen if your central supermassive black hole is pulling in a lot of material and has a strong magnetic field. Then you can get this very bright glowing, you can get these jets of material. Our black hole is not doing that, but there's evidence that it might have been doing that in the past. It might have been pulling in a lot of material in the very distant past, and there's evidence for bubbles in the gas of the Milky Way going out from the center up, above and below the disk that may have been formed from our black hole in the past having pulled in a lot of material, having this strong magnetic field, creating jets coming out.
Yeah.
So
back on the edge of the dinosaurs, basically.
A long time ago. It's good that it's not doing that now because it can get kind of dangerous to be that close to a black hole that's shooting jets out. But it does create these fantastic structures, and we can see those in other galaxies.
And if you just advance once more looking at Centaurus A, you'll see, so just click the trigger, you'll see it just disappears. So basically different types of light allow you to see different things. This is very high energy, this is a gamma ray, so now we really are seeing there's a bright blob of red to the right on the disk. This is a supernovae remnant, a massive star much larger than our sun exploded, and its shockwave is slamming into the gas that was minding its own business. And causing it to glow very energetically indeed. And then finally, one more trigger takes us to essentially the baby picture of our universe. This is the cosmic microwave background. This is a picture of what the universe looked like 330,000 years after the Big Bang. It cooled from that hot Big Bang, cooled enough to actually form atoms for the first time. The light then streamed towards our telescopes. Ever since, we're looking absolutely at one of the furthest views of the sky that we can. From those blotches form galaxies. And if you create universes like I do for a living, you start with that and you learn all the physics you think you know, and then you try to see if you get a galaxy like our own. And when you don't, because you really never do, you then think of new things like dark matter, or you turn to people like Katie and go, what am I missing? And she says dark matter, and you're like, great. Anyways, all of those things are things that you can learn on your own, using the app, using your headsets. You at home, if you don't have the headsets, Google Hardboard, or just, of course, switch it into non-VR mode and look at it that way. We're basically out of time. We've toured the universe. My voice is about to pack in. Could I please get a rising applause for, first of all, our host tonight, Mountain Goat Brewery. Thank you very much, guys, taking a punt on us. Could I get a thanks to our supporters, Osgrave, Swinburne, Castro, and of course National Science Week, Inspiring Australia. Round of applause. Hold on. All of this would not have been possible without the hard work of Rebecca Allen, Alistair Gray, Artem Merv. I can't believe we're here and you know what I'm talking about. We started this months and months ago, of course, and also Carl Knox, Mark Morris, Carl Rombites. Huge round of applause for their efforts in making all of this possible. And finally, before my nervous breakdown and collapse, could you please, with a standing ovation, thank my co-host and co-pilot for this evening, Dr. Katie Mack!
And please remain standing to thank Alan Duffy, who started this whole thing and got this whole thing going.
I'm done. NASA Science Week is over.
Have something to drink, stick around, chat.
Yep.
Yeah, they're not kicking us out yet. Sorry? Oh, the black hole, yes. I didn't see who got who was it? Guess who got the black hole thing?
Black hole, who said the black hole? Oh, that is such a lie, but you both get books. Well done.
2 books.
Thank you all. Hang around, have a chat. There's lots of astronomers. They're wearing blue t-shirts saying Osgrad. Super friendly. Ask them all the questions that we couldn't answer. And enjoy the rest of your NASA Science Week. If you want to hear more science, I'm doing one final talk for NASA Science Week. This is tomorrow at Swinburne. Come along. It's called The State of the Universe, and I'll be a right state. Thank you all, and order some pizza. See you later. Shut the feed! Shut the feed off! Shutting time.
Yeah.